Hello everyone. So in today's video we are going to solve this question. This question is from American Mathematics Competition 2008. So this question says that a sequence A1 B1, A2 B2, A3 B3 of points in the coordinate plane satisfies this condition. So the condition is the an plus 1 comma bn plus 1. This is the ordered pair is equal to the ordered pair square root of 3an minus bn comma square root of 3bn plus an, and it is for n starting from 1 up to, we don't know, for up to here, and it is starting from n is equal to 1 to perhaps 100 in this scenario. And suppose I have the ordered pair a 100 comma b 100 is equal to 2 comma 4, then what is the value of a1 plus b1? It means we have to identify what is the first ordered pair when I substitute n is equal to 0. And when I find that the first ordered pair, I will get the a1 and b1 from there, and then we add the two components of the ordered pair and we get the answer. So in this first look, the question seems that the question is from sequence or maybe some other trigonometric thing, because this root 3 and all this thing is actually indicating to apply trigonometry. Why I'm saying? Because this is an plus 1 we equate with this, and bn plus 1 we equate with that, and from there we take the ratio of an plus 1 and bn plus 1 and we get some trigonometric feeling. But I suggest you to think this ordered pair as the real and imaginary part of a complex number, and from there the question will be easily solved. So at this point you can pause the video and try this question by using the complex number concept, because I think this is the question you must try. Alright, so let's try how the complex number can be applied here. So I'm assuming that the an plus 1, let me change the color first, an plus 1 and bn plus 1 as the component of the real and imaginary component of a complex number. So I'm assuming an plus 1 plus I bn plus 1 as the first order pair left hand side, and it is equal to the complex number which has the real part root 3an minus bn and the imaginary part root 3bn plus an. In this way what will happen, that our intention is to compare the real and imaginary part to equate the an plus 1 with this and bn plus 1 with this. But we can do better. What we can do better is I'm going to simplify the right hand side and I'm collecting the terms containing an together and bn together. How I'm doing it, let's see. Suppose I have root 3an and this is minus bn and plus I root 3 bn and plus an. You can notice this minus 1 here I can write as I square. So by writing this thing, I'm getting root 3an plus iota square bn plus iota root 3 bn plus an. And what it will give you, you can be surprised to notice. Suppose I'm taking this, there's one mistake I done. I have to multiply I here, so I should be there also. So from these two terms, the first term and the last term, you can see that the an is the common factor. So I can take this an as a common factor. So I am getting root 3 plus I an. And from the middle two terms, I am getting the b and I as the common factor. So I'm taking the bn times iota as the common factor. So I will left with this thing as root 3 and plus again I. So you can notice now the root 3 plus I is now a new common factor. There is a an plus bn iota times root 3 plus 1. Now you can identify what is happening here, and for that let me first give you some basic introduction of rotation and the scaling factor. So let me write this first, and this is what an plus bni and root 3 plus I. So we have to be very careful. We have to deal with this, but we deal with this equation or the complex number equality smartly. And what I'm saying is this thing. Suppose I have this thing is the note or the concept, whatever you can say. Suppose I have to find the z2, and z2 is a complex number which is z1 times e to the power I theta. What is the meaning of this? I don't care what the angle of z1 has, but whatever the angle the z1 possesses, let us say this z1 is actually taking the argument. Let us say it's the magnitude r e to the power I theta 1. So when we multiply, we get r times e to the power I theta plus theta 1. It means now the z2 is the theta 1 unit rotated z1. Because now what happens that the magnitude remains same as the magnitude of z1 was there, but the angle is moved by theta 1, moved by theta, not the theta 1, moved by theta from the previous theta 1. So this e to the power I theta is a rotating factor which rotates the z1 theta unit anti-clockwise away from the original place or original situation. So meaning of this thing, what I want to say graphically is, suppose I have the z1 here, and if I multiply e to the power I theta, the z2 is nothing but this is theta 1 and this gap is theta. But in that case the magnitude remains same. But sometimes what happens, suppose I'm going to do this thing, I'm multiplying this entire thing by, let's say here, some magnitude of z2. So what is the meaning of this? Magnitude of z2 means now this is a new number. So you are also multiplying and then you are scaling up also. It means, or let me just take some different example. Suppose I multiply here 4. So what happens that this is our original vector or maybe the complex number. This is responsible to give the rotation theta unit away from the original position, and this 4 is responsible to scale it 4 unit longer, or maybe this is the lesser than 1, that will be scale it down. So this is the scaling factor and this is the rotating factor for this complex number or the complex vector. So in the same way, can we understand this whole scenario here? So let me just take the copy of it and let us try to understand. So how do we understand? Let's think. I have this original position, the an plus bni. So let me write it here in this way, that the an plus 1 plus I bn plus 1 I can write as an plus bn I. And I want to write this root 3 plus iota in its Euler form. So how do we write it? This is root 3 by 2 plus 1 by 2 iota. And this can be easily written as an plus bn I. And this is e to the power I pi by 6. But there, one thing I did mistake is I have to multiply this entire value with 2 because I have divided by 2. So I'm multiplying this 2 here, so it will be there. And now try to read this whole scenario. So whatever I have the complex number initially, and whatever its position is there in this Argand plane, you are rotating by pi by 6 unit away anti-clockwise, and you are scaling by 2 unit up. So the meaning is that suppose I have to find the second ordered pair in this whole series or the sequence. I have this an plus 1 plus I bn plus 1, and let's understand it graphically. So I have somewhere, I don't know where the a1 and b1 lie, so let us take this is somewhere here, and I don't care what the angle it has. Let's say this is theta. So this is the ordered pair a1 b1, that is a complex number z1. Let's say z1. z2 means that when I substitute n is equal to 1 there, that will give you a2 comma b2, and this is 2 times the a1 plus I b1 and e to the power I pi by 6. So what is happening that when we are taking, let me just take this thing down a bit, just behold. Okay, I've taken this down just to show that how the scale factor is acting. So I have this vector here, and when I multiply this thing to that, here I'm multiplying, it means now it will rotate pi by 6 unit anti-clockwise away, and also 2 unit scale up. It means now if you have to find the position of a2 b2, it will be like this. I don't know how it will look, but I'm sure that it is schematically like this. So this is the position I have of a2 b2, and it is actually pi by 6 unit away from the original position, and also twofold scaled. In order to find the a3 b3, now you get the idea what will happen. To find a3 b3, it means I have to find n is equal to 2 at this value, so it will become a3 plus I b3, or you can say a3 b3, doesn't matter. And what will happen? You are now getting this as twice of a2 plus I b2 and e to the power I pi by 6. So what is happening? You already had a2 b2 here. You already had a2 b2 here. Now one more time again you are scaling it 2 unit, but at the same time you are rotating by pi by 6. So again pi by 6 rotate the same and scale it 2 unit up. So this will be the position somewhere here, a3 b3, and the sequence goes on and goes on. So what is the pattern we can extract? Let's try. So what is the pattern we are extracting? That when we are going to do, let's say this is your z1. I have written z2 there, why I don't know. This is z1, by the way, sorry. This is our z2. So in order to find the z2, what we are doing, we are getting twice of the z1 and e to the power I pi by 6. Notice that there is a multiple 1 there hidden here. This is a multiple 1 pi by 6. In order to get z3, you are getting twice of z2 and e to the power I pi by 6. but Z2 is already this in terms of Z1. So you can see that it become 2 square Z1 and e to the power I 2 pi by 6. Notice that this factor here 2, this power here 2. So can we guess what will happen for Z4? For Z4, I will have 2 to the power 3 Z1 and e to the power I. Then this will become 1 less than the coefficient here, or the subscript here, that is 3 pi by 6. This is the way the pattern is moving. This is here 3, this is here 3. So when we relate this to then power 1 and then 1 here, then 3, then their power here, that is 2 and there is 2, and here subscript 4 3. So I have to find the A100. So to get this thing, the A100 comma B100 is equal to 2 to the power 99, because there's 1 less than that, and Z1, and Z1 is nothing but A1 plus IB1, and into e to the power, again there 1 less than the subscript here. So here subscript is 100, so again the coefficient of pi by 6 here on the top will be 1 less than the 100. So this will become I and 99 pi by 6. So what is happening there? A100 comma B100 is already given to you as 2 comma 4 in the question. It means I can safely replace it by 2 and 4 respectively. So 2 comma 4 must be equal to this quantity, so 2 to the power 99, and this I can evaluate. So let me just write this first, then we will evaluate it also. This is nothing but e to the power I, and this is 33 pi by 2. So 33 pi by 2. So 33 pi by 2 is an odd multiple of pi by 2, or we can write it as 16 pi plus pi by 2. So 16 pi plus pi by 2 lies in the first quadrant, so it is equivalent to pi by 2. Let me just clear this thing. A1 plus IB1. You can write this thing as 16 pi plus pi by 2, and this remains same, A1 plus IB1, and here this will, we can write as I 16 pi into I pi by 2. You can notice that this value is 1 only, because this will turn into cos 16 pi plus I sine 16 pi. So cos 16 pi is a cos even pi, that will give you 1, and sine 16 pi will give you 0, so this will give you 1 only. So we are left with this, and this will give you cos pi by 2 plus I sine pi by 2. So that is going to be I. So I can write safely this whole thing as I here. So this is nothing but 2 to the power 99 and A1 plus IB1 times I. Now I have 2 comma 4 on the left, and this is 2 comma 4 or 2 plus 4i, doesn't matter. Just for the sake of like convenience, I'm writing like this, and minus B1 if you multiply I. You can now compare the real and imaginary part both sides to get A1 and B1. So for the real part, I'm getting minus B1 times 2 to the power 99, because when you multiply this to that, that will be the real part independent of iota, and this is 2 is the real part on the left hand side. That must be equal to 2. So from here, I'm getting the B1 as negative of 2 by 2 to the power 99, that is negative of 1 by 2 to the power 98. And when we compare the imaginary part, so you get A1 times 2 to the power 99 is equal to 4. So this time I'm getting A1 is 1 by 2 to the power, there's 97. And now I have to add them. So I have a1 plus b1 is equal to 1 by 2 to the power 97 minus 1 by 2 to the power 98. From there, I can take 1 by 2 to the power 97 as a common factor. That will leave us 1 minus 1 by 2. This will again turn this as 1 by 2. So 1 by 2 into 1 by 2 to the power 97 will be 1 by 2 to the power 98. And that is our desired answer. So that was the question for today. In the next video, we will come up with some other question, because I believe these are the questions you must try. Stay math active.